All right, good afternoon, everybody.
Wait, let me introduce you. Just wait.
Okay.
In fact, should we wait a minute just in case? Or maybe, okay. All right, let's start. So we are very happy to have Dmitrii Pedchenko from Penn State, who will tell us about the Picard group of the moduli space of vector bundles on the quadric surface.
All right, good afternoon, everybody. So let me start by thanking the organizers for the opportunity to speak. I will be telling you about the Picard group of the moduli space of vector bundles on the quadric surface, which is based on my paper that I posted on in the summer to archive. So for starters, let's fix a smooth projective surface. Let's call it X, and let's fix an ample divisor on it. So one thing which is unfortunate is that I'm going to be using a slightly different notation from empiric. So I apologize for that, but hopefully we can still pile through that. So the key notion we'll use is the notion of the slope for vector bundle V. Let's set the slope mu to be given by this number, where you take the first Chern class of your vector bundle, intersect it with ample divisor, and then divide by the rank. That's just a number. And with this notion, we can define a stable bundle. So a stable bundle is such a bundle that any sub-bundle has smaller slope. So if you want to speak about semi-stable bundles, you replace this strict inequality by less than or equal to. And basically, the key fact and the only fact we're going to use about semi-stability is that if you have two semi-stable bundles, V and W, and the slope of one is higher than the slope of the other, then there are no homomorphisms in this direction. And then, of course, everybody is familiar with the following celebrated results of many people, that if you fix the numerical invariance of your vector bundles, so in the case of a surface, you might want to just fix the rank and the first two Chern characters, Chern classes or characters, then there is a projective moduli space for semi-stable bundles on X. So here, for simplicity, I'm speaking about just the usual semi-stability and vector bundles, but if you are familiar with Gieseker stability, and you can also mentally replace bundles by sheaves, all the results apply. But to avoid technicalities, I'm going to be using this language. And so what I'm going to be interested in, I will be interested in trying to compute the Picard group of the moduli space when the surface I'm looking at is the quadric surface P1 cross P1. So here I'm not specifying the ample divisor just yet. I'm going to say a few more words later on. And while we're still on this introductory slide, let me say that there's been previous work done on the same problem. So Nakashima and Kin, they considered the moduli space, but with restrictions on the rank of vector bundles. So they considered only vector bundles of rank 2. And then Yoshioka, he considered higher rank vector bundles, but then with restrictions on the first Chern class. So the goal of my work was to calculate the Picard group for as many Chern characters as possible. So on the next slide, I want to talk about the main tool for constructing line bundles on the moduli space. So this goes under the name of the Downson homomorphism. And this Downson homomorphism is done like this. So suppose you have a flat family of bundles of some fixed character on your variety X. So in other words, you just have a vector bundle on the product X cross S. So then you can start with the K group and produce an element in the Picard group of the base space S via the following pull, push, or Fourier-Mukai type procedure. So you take an element in the K group of X, let's say you take a vector bundle E, you pull it back to the product along Q, then you tensor it with the family of bundles U, and then you push it down to the base space S. So you'll have something in the K group of S here, and then you just take the determinant, and this way you'll get the line bundle. So ideally what we want to do, we want to apply this construction to a universal family of semi-stable bundles on our moduli space. If it exists, if it doesn't exist, then somehow still perform a similar construction. And it turns out that this Downson homomorphism doesn't work on the nose because of the ambiguity in the universal family. So the universal family is defined up to twists by a line bundle from the moduli space. So in order to avoid this ambiguity, you need to restrict the domain of the Downs and homomorphism to be this orthogonal component to the Chern character you're looking at. So you're looking at all the classes in the K group which pair to 0 under the earlier pairing. And then Downs and homomorphism gives you a natural way to construct line bundles on the moduli space. Okay, are there any questions so far? So if it's good, then what I first want to do, I want to first contrast my results to the results obtained by Dmitrii in the 80s in the P2 case, because it's just going to be instructive to compare the two results. So in order to tell you the story about the projective plane, let's just recall some well-known definitions. So the definition of an exceptional bundle, everybody knows, of course. So I just wanted to point out that on Del Pezzo surfaces, exceptional bundles are also semi-stable, which I'm going to use to obtain the vanishings of homomorphisms, just as I noted at the first slide. Another technicality we'll have to do is to repackage our Chern character into the so-called logarithmic invariance, where this letter nu is called the total slope, where I just take my C1 and divide by the rank. And the second logarithmic invariant is the discriminant delta, which is given by this formula. If you know what Bogomolov inequality is, then precisely this delta appears, precisely this discriminant appears in Bogomolov's inequality as well. So with this notation and this definition, we have the following theorem of Drizay and Lepotier, and here you can see precisely the curve which was discussed during the previous talk, but not shown. So what Drizay and Lepotier proved in '85, they proved a characterization of when the moduli space is positive dimensional purely in numerical terms. So their theorem states that in order to have a positive dimensional moduli space, the Chern character V should satisfy some numerical equation. The discriminant should be greater or equal to some function of the total slope, which I call DLP for Drizay-Lepotier. So you can see this, this curve down below. Horizontally, we have the total slope, vertically the discriminant. And then what the theorem says is that the characters for which the moduli space is positive dimensional, they can be sitting either on the Drizay-Lepotier curve somewhere here or above it in this gray shaded region. Okay, so I wanted to also say a few words about how the Drizay-Lepotier curve is constructed. As you can see, it's comprised of various branches, so these mountain peaks, if you wish. And those mountain peaks, they're given in terms of exceptional bundles. So for instance, if you look at this peak over here, underneath it, you will find the numerical invariance of line bundle O of 1, which is an exceptional bundle. Underneath this peak, you'll find exceptional bundle O. Underneath this peak, you'll find some exceptional bundle of total slope 1/2. That's some twist of the tangent bundle to P2. And here, slightly more rigorously, I show how those peaks are actually constructed. So if you find an exceptional bundle which is close to the, in terms of the slope to the Chern character we're looking at, so it's sandwiched like this between 0 and 3, then you actually have two vanishings. So homes from E to V, they vanish by the semi-stability of both E and V, and the fact that the slope of E is greater than the slope of V. Then X2 also vanishes by Serre duality and semi-stability. So this 3 here, it is the slope of the canonical bundle. That's why Serre duality works here. And from these two vanishings, you get that the Euler characteristic is less than 0 like this. And using Riemann-Roch, this just produces some numerical condition, some numerical relationship between the discriminant and the total slope nu. So one thing I want to add is that if your character happens to lie on the DLP curve, then we have equality here. So the Euler characteristic from E to V is 0, or in other words, delta is equal to DLP. So I want to say a few words about this situation when the character happens to lie on a branch of the Drizay-Lepotier curve here. So in this picture, you can see that V lies on a peak corresponding to O of 1. In this case, we want to say that this exceptional bundle O of 1 is associated to the Chern character we've picked here. And from what I said on the previous slide, this implies that this Euler characteristic is 0. And if you add that to the vanishings of homes and X2s, this shows that actually all X groups vanish. for the associated bundle. And this means that if you go back to the definition of the Donaldson homomorphism in terms of this pull-push formula, if you apply the Donaldson homomorphism to the associated bundle and use base change in cohomology, the pull-push actually vanishes already in the K group. And then when you take the determinant, you produce the trivial bundle. So in this sense, exceptional bundles associated to a Chern character, they are the natural candidates for lying in the kernel of the Donaldson homomorphism this way. And what Dmitrii proved in '88 is that this is all the story. So if you consider the moduli space of positive dimension, and these are the only ones with interest in Picard groups, then if you're above DLP and there is no associated bundle in terms of this definition, then Dmitrii actually shows that the Donaldson homomorphism is an isomorphism. So we just need to recall that the orthogonal complement to V inside the K group, which is rank 3, becomes rank 2. So the Picard group is Z2. On the other hand, when the character happens to lie on the Dmitrii-Lapotier curve, then as we discussed, we will have an associated exceptional bundle. And as I just told you, it naturally, or rather its dual, lies in the kernel of the Donaldson homomorphism. And then there is all there is in this case. So to see that the Picard group must be Z in this case, you can argue like this. So your V perp is Z2, then lambda is surjective, and you know that one copy of Z is killed by this associated bundle. So the Picard group can be no larger than Z, but it must be Z because the moduli space is projective, therefore it has an ample generator giving you a 3 abelian group inside of it. So that's the P2 story, which could be summarized by saying that the Picard rank is totally controlled by exceptional bundles. So now we are finally ready to move on to the case I was interested in, the case of the quadric. So the results about when the moduli space is positive dimensional, they carry over by the theorem of Rudakov, which again says that there is some numerical condition on the discriminant and the total slope, which characterizes positive dimensional moduli space. So here, this is the polarization I'm using. The anti-canonical polarization would be just F1 plus F2, but in this case, the moduli space wouldn't be nice enough for our purposes. So we perturb one of the components a little bit to get a nice moduli space. And another remark is that the total slope now has 2 components because the Picard group of P1 cross P1 has 2 components. So if you want to visualize the graph of the DLP function in this case, the plane of totals, you have the plane of total slopes this time, and then the discriminant is vertical. And the graph of DLP now looks like this surface. But otherwise, this surface has a lot of the same features as the Dmitrii-Lapotier curve for the P2 case. So in particular, this surface is comprised of various branches. So for instance, here you can see the orange branch, here you can see the blue branch, and here you can see the green branch. And the branches are again, excuse me, given by the exceptional bundles. So somewhere here underneath the orange branch, there is a line bundle defining this piece of the DLP curve. Somewhere here in the corner, there is an exceptional bundle defining for you the blue piece of this surface, and so on. And so if you look at this surface long enough, you will notice that the situation is slightly more complicated in the P2 case if you think about how a character could be positioned with respect to the DLP surface. So this time we have 3 possible cases. On the one hand, your character can be positioned strictly above the DLP surface, or it can be positioned on one branch, on a single branch of the DLP surface, so maybe somewhere here. And then there's going to be a single associated exceptional bundle given that branch. Or in fact, it can be positioned at the intersection of 2 branches, so somewhere here along this line. Then you'll actually have 2 associated exceptional bundles, one for the left branch, so somewhere here, and one for the right branch somewhere underneath here. And so once you understand that, you might naturally think that, okay, maybe similar to the P2 case, I have now 3 cases above on one branch and on 2 branches, and the answer will be entirely controlled by the number of associated bundles you have. So no associated bundles above, one associated bundle on one branch and two associated bundles on two branches. And the central kind of result we obtain is that actually this is not the case. So the classification for the Picard group is not entirely controlled by the associated exceptional bundles or by the position with regards to the DLP surface. So in the first case, when we're above DLP, we can show that again, the Donaldson homomorphism is an isomorphism, and therefore we just calculate the rank of VPerp. It is Z3 now because the K group for the quadric is Z4 and it's a hyperplane. And therefore, in this case, the Picard group is Z3. Then in the case you're on two branches, so maybe think of a character somewhere here. There are two associated bundles, Z1 and 2. They both lie in the kernel, so they kill off two copies out of the Z3, and you're left with just Z. And then the most interesting case is when you're just on a single branch of the Drusela-Poitier surface. Then on the one hand, you have a single associated bundle that lies in the kernel. And then in this case, in some cases, you can find characters for which the Picard group has rank 2. But we can also construct like sporadic churn characters for which the Picard rank further drops to Z, and the kernel is something larger than just the group generated by the exceptional bundle. So really, this is the interesting part over here. So what I want to spend my time on in the rest of the talk is to explain a little bit the dichotomy arising between these two cases when you're in a single branch of the DLP surface. And provisionally, I will call the first case, the kind of anticipated case, the good case, and this unexpected case, I'll call the bad case. These are maybe not the best names, but this is the ones I'm gonna use. Are there any questions so far? Okay, if not, I'll give you two explanations for why the Picard rank drops. So one is an easier explanation. So if you take this concrete churn character of rank 4 with these numerical invariants, then you can picture it on the graph of DLP surface over here. So this, as you can see, this W1 character, it indeed sits on a single branch of the DLP surface on this orange piece. And this orange piece is given by the exceptional bundle O, by the trivial bundle. So I say here that line bundle O is associated to V. Well, in this case, you can resolve your semi-stable bundles of that character in such a particular way, then you can show that the moduli space is just a projective space. And that's why the Picard group is Z. But then you can do even more. You can construct an infinite sequence of churn characters for which the Picard rank drops. So here on the picture, you can see this infinite sequence. So W1 was obtained as the sum of two characters with symmetric C1, V1 and V2. And then you obtain W1. Then you can take a sum of V1 and W1 to get a W2. Then you get this, you can take a sum of V1 and W3, and this way you're going to get a sequence accumulating towards V1. And as you can see from this picture, which is just a top-down view on the Drusela-Poitier surface, all of these characters lie on a single branch of the Drusela-Poitier surface. And there's nothing special in choosing this line. There's a symmetric line over here, and in fact, you can even change V1 and V2 in a certain way to get other lines with infinite sequences. But still, these bad cases, they are somewhat sporadic. For most churn characters lying on a single branch of the DLP surface, the Picard rank will be 2. So this is really something special happening here. So for a second explanation, and one thing I forgot to add is that when you start constructing this infinite sequence, you can actually show for the certain initial segment of this sequence that you still get projective spaces for your moduli space, but the computation becomes more and more complicated because W1 is the moduli space of dimension 3, but then the dimension grows very quickly and the resolutions become unwieldy. So it's harder and harder to show projective space. But in general, the idea behind the proof is like this. So in order to show some results about what the Picard group is, one starts by building a family of vector bundles parameterized some base T. So we want two properties from this family. First of all, we want the resolutions to be simple in some sense, to be convenient. And another property we want to have is that this parameterizing base is not complicated. So it's something simple so that we can work with it. Then at the second step, you usually prove that the Picard group of the moduli space is then isomorphic to the Picard group of the semi-stable locus, but also taking into account the natural group action on your resolutions. So you want to establish the isomorphism between Pic of M and Picard group of G linearized line bundles on the semi-stable locus. And then the last two steps finish the computation. So as I said, if T is simple enough, we can estimate its Picard group of linearized bundles by using a little bit of group actions and GIT. And then the hardest part of this program is analyzing the unstable locus. So two things you want to usually prove about the unstable locus is what's its codimension and whether it's irreducible. So codimension requires some shot stratifications with Harder-Simhan filtration, and it's usually not trivial. And showing irreducibility turned out to be a hard thing. And then once you have these 4 points established, you can tackle your good case and bad case. So here I assume that my Chern character lies on a single branch of the Druzé-Lepotier surface. Then one can actually show that the codimension of the unstable locus is greater or equal to 2. And then you have this chain of isomorphisms. So this is step 2. And this is this codimension 2 assumption. And you get just that that's the Z2. While in the bad case, the thing that goes wrong is precisely the codimension of the unstable locus. In the case of the bad character, one can isolate an irreducible divisorial component in the unstable locus. And therefore, if you look at this restriction sequence, you can see that one copy of Z will be killed off and the Picard rank will drop. So I think that's mostly what I wanted to say. I just want to add that these results have very kind of computational flavor to them. They are not very abstract. In fact, to figure out, if you start with a Chern character V to figure out what is the Picard group, there is a finite computational procedure to do that. So in finitely many steps, you compute whether your character is above DLP on one branch or on 2 branches. And then further to tell whether you're in the good case or in the bad case, you again look at the numerical invariance of your Chern character, and it's some numerical condition using Riemann-Roch theorem to tell you whether you're in case A or in case B. And this way I implemented a lot of computations like that on a computer. So thank you. I think I want to stop here, and I'd be happy to answer any questions you might have regarding this presentation.
Thank you, Dmitrii. Are there any questions?
This theorem is slightly simplified from the truth. Can you just in interest of full disclosure say what needs to be adjusted?
Yeah, so like I stated it in this clean way for simplicity. In fact, so the way I stated, you're either in these 2 cases, either in case A or in case B. So the numerical conditions, yeah, will tell me whether to look at case A or case B. And then in case A, I will always get the Picard group equal to Z2. But in case B, I can only show that the Picard rank drops to Z for certain infinite sequences I spoke about, but not universally. So you can kind of start with a Chern character V for which there will be this divisorial component in complete families of vector bundles. But for certain special characters, I don't know how to show that it's a Z. So really here, this subcase B doesn't cover all of the characters satisfying this bad numerical conditions, and only a subset of those. So only
but the
really
Picard rank is correct,
infinite
right?
sequences constructed like this. But the Picard rank is correct, right?
Okay.
So if you further impose primitivity assumption on your Chern character, then those results are universally true. So it's a certain, you need to fiddle around a little bit if you don't know that the character is primitive. Yeah.
So in case B, is there like a nearby Bridgeland moduli of Bridgeland stable objects that sort of has Picard rank 2?
This is a good question, which I haven't really thought through. So I was kind of thinking in the other direction. I was thinking in the direction of what happens when you kind of cross the anti-canonical wall here, if you flip 1 plus epsilon to 1 minus epsilon, things like that. But I haven't really considered Bridgeland stability conditions. I don't know, maybe the fact that it's a P3 on the nose like that can tell you some additionally, but I don't know the answer to that question really.
It looks like it's possible to be on 3 different faces of the surface. Is that true? Because you only said up to 2.
No, it's not true. It's the same as with the usual Drizella-Pottier curve for the P2 case. Certain in triple intersections, it might look like they appear, but they lie in this fractal region, so the coordinates of your Chern character won't be rational, and there will be no actual characters of actual bundles.
Or they happen at an exceptional bundle.
Yeah, but exceptional bundles, they lie underneath this surface, and in any case, yeah. Mm-hmm.
So you can have triple intersections, but then the moduli space is a point and the Picard rank is 0. Right, so it cuts it down by 3.
Oh, yeah. Mm-hmm.
All right, if there are no other questions, let's thank Dmitrii again. I'll make noises. And maybe we'll take a 5-minute break and be back at 11:50 for an Henna's talk. Henna, is that okay?
Yes, sounds good.
All right.
Okay, stop recording.